Hi everybody, today I'm going to show you an example of Dijkstra's algorithm. We'll use it to find the shortest path between vertices. For a way to graph, the first thing we're going to do is pick our beginning vertex. I'm going to use vertex A. We set the beginning vertex as having a distance of 0 from itself. Then for all the other vertices, because we don't currently know the shortest path, we just set the distance to be infinity. So we put that on all of the vertices until we find a shorter path. Then from our vertex A, we'll look at the adjacent vertices. In this case, we have B and C. If we look at the path from A to B, we can see there's a distance of 4. This 4 will replace the infinity because now we have a number that we can put in as a path. We'll do the same thing from A to C. We have a distance of 2. 2 is less than infinity, so we do a quick replacement. Now we want to compare our two values. We have 4 and we have 2. 2 is less than 4, so this becomes the next vertex that we work from. C to B has a weight of 1, but remember, we're coming from a value of 2, so now this path has a weight of 2 plus 1, which is 3. 3 is less than 4, so instead of doing our direct path from A to B, which was 4, we could go in this smaller path, A to C to B, which is 3, so we're going to replace that 4 with a value of 3. Now we can look from C to D. C to D is 8, but we're adding the 2, so 2 plus 8 gives us 10. Now that we have a numeric value for a path from A to D, we'll get rid of the infinity and keep the 10. Let's do the same thing from C to E. From C to E, we have a weight of 10. 2 plus 10 gives us 12. We'll get rid of the infinity and put in our 12. Now we look at our three values. We have 3, we have 10, and we have 12. We're going to pick the smallest, which is the 3, which says we'll repeat this process again working from B. To help us keep track of what we've done, I'm just going to mark off the vertices we don't have to look at anymore. We're done with A, we're done with C, we won't use them anymore. We're only going to look at other vertices that are adjacent to B. From B, there's only one adjacent vertex we need to look at, which is D. The weight from B to D is 5, but remember, we need to add that to the 3. 3 plus 5 is 8. 8 is less than 10, so we'll flip that number out. This says B is also finished, and now we're working from D. From D, we need to look at both E and F. To go to E, we're going to add 8 plus 2, which gives us 10. Then D to F will be 8 plus 6, which gives us 14. For vertex E, our new path of 10 is shorter than the 12 we had previously, so we're going to switch that out to say now we have a shorter distance of 10. For F, we previously had infinity, so we know we can put the 14 in for our path for F. Comparing 10 to our distance of 14, we can see that 10 is smaller, so E becomes the next vertex we work from. We can say D is finished, which says we only now are looking at E and F. We can see the distance from E to F is 3, so we'll add our 10 plus 3 to get 13. 13 is less than 14, which says now we've found a shorter path from A to F, and we have completed our graph. Let's do a quick wrap-up of what we found. Now we can write in the shortest path from A to each of the vertices. From A to B, we have 3. From A to C, we have 2. From A to D, we had 8. From A to E, we had 10, and A to F is 13. Remember, when you use the algorithm to build solutions, we're doing it one small step at a time. Once a vertex is finalized, its shortest path is locked. If you follow this same process carefully, you can solve any similar problem.